Hi, you are welcome. Today we'll discuss one reaction which came in GATE 2021. The shape of this compound ClF3, XeOF2N3 and XeO3F2. So this question can be explained with the help of VSE pair theory, that is valence shell electron pair repulsion. So in this theory, we'll calculate the structure by calculating the total electron count, static number of lone pairs, sigma bonded electron, pi bonded electron. We'll calculate this, and finally we'll determine what through interaction, which interaction will be more favorable in structure. We'll determine, and from this we'll determine the most stable structure. So for Cl, the total electron count at peripheral will be calculated. So Cl, the valence electron count is 7. For 3 fluorine it is 3. So total electron count equal to 10, electron pair equal to 5. Now this 5 is will be 3 sigma plus 2 lone pair. Now from this we'll calculate the static number. Static number is equal to number of sigma bond pair electron plus number of lone pair electrons. So here 3 number sigma bond pair electron is 3 and lone pair electron equal to 2. So Sn will be, static number will be 5. So for 5 static number, the geometry will be TBP, that is trigonal bipyramidal. For TBP type geometry, it will be TBP type geometry, trigonal bipyramidal geometry. So now here 3 combinations are possible, where these 2 lone pair may be in axial or maybe in equatorial as in C, and maybe one axial in one equatorial as in B. So we'll calculate the interaction, the lone pair, bond pair, and bond pair interactions from these 3 structures, because this interaction determine the whose structure will be more stable. So here the lone pair interactions are at 180 degree. So one lone pair interaction at 180 degree. In structure B, the lone pair interaction are at 90 degree, one at 90 degree, and in structure C, the lone pair are in 120 degree, so one at 120 degree. In according to VSE pair theory, the lone pair interaction is much more stronger than lone pair bond pair, which is much stronger than bond pair. So when it is at 180 degree, so it is quite lesser, and when it is at 90 degree, it is quite larger. So this will be quite unstable. So we'll eliminate the structure B. Now between A and C, we'll see we'll move to lone pair bond pair interactions. So here the lone pair interacts with this 3 fluorine at 90 degree, and also for the case of this lone pair, so total 6 number of interaction at 90 degree. In case of we'll eliminate B. Now in case of C, the lone pair, this lone pair interacts with this fluorine at 90 and this fluorine with 90, and also this lone pair, so total 4 interactions will be there at 90, and 2 interaction at 120. So as the 6 interaction 90 is quite unstable, so this is the preferred structure C, where the lone pair are in equatorial position. So one shortcut is there. If you see the lone pairs, when the lone pairs are in equatorial position, this is quite stable structure, because in equatorial they are getting more space to accommodate. XeOF2 is xenon will have 8 valence electron, oxygen 2, and for 2 fluorine 2. So total electron count will be 8 plus 4 12. So electron pair equal to 6. So 6 electron pair will be 3 sigma plus 1 pi plus 2 lone pairs. So static number will be equal to number of sigma electrons pair plus number of lone pair electrons. So 3 plus 2 equal to 5. So geometry will be TVP. Now in TVP geometry, for this case of XeOF2, 5 numbers of geometry is possible. As you can see, A, B, C, D and E. Now in A, both the lone pair are in equatorial and the multiple bonded oxygen is also in equatorial. In B, the multiple bonded oxygen is in axial. In C, the one lone pair is in axial. In D, both the lone pair in axial. And in E, one multiple bonded oxygen and the lone pair is in axial. Now from the previous structure, we'll see that the lone pairs are generally preferred in equatorial position, and also this rule is applicable for multiple bond, that is double bonded oxygen. So double bonded oxygens and the lone pair both are preferred in equatorial position, because multiple bond will have 4 electrons, and multiple bonded interactions with lone pair, either lone pair or bond pair, will be stronger. So it shall be minimized. So in case of E, as one lone pair and multiple bond are in axial, so this will be eliminated. In case of D, also 2 lone pairs are in axial, so it will be eliminated. In case of C, one lone pair is axial, so this will also be eliminated. And in case of B, one oxygen is in axial, so this will be eliminated. In case of A, where 3 are in equatorial, 2 lone pair and oxygen is equatorial, so this will be the preferred geometry. Now we'll see the next question, XeO3F2. For Xe, total electron count at valence shell equal to 8. For 3 oxygen it will be 6, and for 2 fluorine it will be 2. So total electron count equal to 16. Now electron pair equal to 8. Now for this 8, it will be 5 sigma plus 3 pi. So steric number equal to, and for 5. Now geometry will be TVP. For TVP structure, the possible alignments are A, B, C. For A, where the 2 fluorine are in axial position. In B, the fluorine are in equatorial position. And in C, one fluorine is equatorial and another is in axial position. Now if we apply the previous rule, that multiple bond generally prefers to occupy in equatorial position. So in case of A, where the 3 oxygen are in equatorial, so here the interactions will be lesser and this will be more stable. But in case of B and C, here both the oxygen are in axial position, so interactions will be stronger at 90 degree. So this will be not favorable, and in this case it will also be not favorable. So in case of N3 minus, N3 minus will be, the structure will be like this. This is plus, formal charge will be this. It will have resonating structure. And another resonating structure will be this. This is this. So here in this structure, this nitrogen is sp hybridized and this two are sp2 hybridized, If we see the orbital diagram for this nitrogen, this is the central nitrogen. This is the peripheral. This is 2py and 2pz. Let's see, the x-axis is the bond axis. If this is py and pz, this is py, so this overlapping will take place to form a pi bond, and here this is pz, so this pz will overlap to form another pi bond. The spin will be in opposite direction. So this is the structure of N3 minus. It is linear. So ultimately, if we move back to the question, this is the question: the shape of this molecule. So ClF3. This is the preferred structure. This is T-shaped. We will eliminate the lone pair to calculate shape. So this is T-shaped. This is T-shaped, and now for XeOF2, this is preferable. So this is also T-shaped. And N3 minus is linear, and XeO3F2. This is preferable. So this is trigonal bipyramidal. T-shape, linear, trigonal bipyramidal. So A will be correct answer. Guys, if you have any doubt regarding this video, please let me know in comment box. Thank you.